Thank you very much. Yeah, as he said, my name is Dilano Saldin. I'm from the Department of Physics at the University of Wisconsin-Milwaukee. I was asked to talk about single particle reconstruction algorithms. I should say at the outset that there are others who are doing this, so I will only be talking about our approach to the problem. But here is the problem. The problem is actually very different from even that of nanocrystallography, as there are no Bragg spots to provide orientation information. What you see on any particular diffraction pattern is a diffuse intensity distribution. And we are supposed to determine the particle structure without even knowing its orientation at the outset. Now, there are some people who work on first trying to determine the relative orientations of the particles corresponding to each diffraction pattern. But as I will point out, this is not very helpful if you're illuminating a large number of different particles, because the particles don't have a fixed orientation. Now, there's another problem, and that is that the signals we expect are going to be very weak. So let's understand this by starting off with nanocrystallography, which is a very successful technique. But in nanocrystallography, there are perhaps 1,000 molecules per nano. And when one goes from there to a single particle, the intensity falls by a further factor of n squared, which is 10 to the minus 6. And this is basically because the Bragg reflections go up in intensity as n squared, whereas for a single molecule, the intensities are essentially incoherent, and therefore it falls by a further factor of 10 to the minus 6. Now, of course, most of the initial studies have been on viruses, which contain a large number of proteins. So let's suppose a typical virus has, say, 10 to the 3 proteins. So this bridges the gap a little bit, but there's still a further gap of 10 to the minus 3. But this can be overcome by averaging over the perhaps 10 to the 6 diffraction patterns that one has. Since the signal to noise probably increases by a factor of a square root of n, where n is the number of diffraction patterns, as one averages over diffraction patterns. So you can get probably all the way to a useful pattern at the end. Or else one has to be satisfied with lower resolution as the intensity increases as Q falls. So the particular approach that I will try to talk about today is to reconstruct the diffraction volume without even determining the relative particle orientations corresponding to each particular diffraction pattern. This allows the method to be used also for multiple randomly oriented particles. And this talk will only be about our approach. Here are typical diffraction patterns. On the right, you see a typical diffraction pattern you would expect, which corresponds to about 4 times 10 to the minus 2 photons per pixel, plus shot noise. Whereas if you have a noise-free simulation, the pattern looks more like the one on the left, which is more continuous, with of course, the central Bragg central beam stop in the middle. But so our typical patterns are like the ones on the right, and it is necessary somehow to do some averaging with the patterns on the right to produce a more continuous looking pattern so that we can analyze it. Now on this point, I want to get into a little bit immediately into the idea of Poisson noise and the mean of the correlations. So as I said, in any particular diffraction pattern, you will see m counts or n counts on any particular pixel. Now the probability, now the average value of the mean count, if you like, is the sum of the n's with the probabilities of all the n's, and this mean count is equal to the quantity lambda. So if you got 2 counts, m and n, on two different pixels, we want to take the product of M with the P of M corresponding to some mean value lambda 1, and N corresponding to the P of N corresponding to lambda 2, the mean value lambda 2. And here's the remarkable thing: this product can be written, be separated in such a way that each term is lambda 1 or lambda 2. So as a result of this averaging over a large number of diffraction patterns, one obtains the product of the expected intensities lambda 1 and lambda 2 on those two pixels. So this is the expected value if there was no Poisson noise. Okay. Yeah. So one other thing, although as I said, the M and the N typically have values of about 10 to the minus 2, you might think that a product of M and N will produce a value of 10 to the minus 4. But on the other hand, you average over 10 to the 6 patterns. So 10 to the minus 4 times 10 to the 6 is about 10 to the 2, i.e. about 100. And at that level, when you get a signal of about the order of 100, this is the sort of level which is generally unaffected by Poisson noise. This is what I mean by averaging over a large number of patterns. Now, before I go on, I want to illustrate the technique with a two-dimensional example. So a two-dimensional example would be a membrane protein in a membrane. Now, often membrane proteins have a hydrophobic part which lie within the membrane, and hydrophilic parts which lie outside the membrane in a real cell. So the hydrophilic part likes to live in a watery environment. The hydrophobic part likes to live within the membrane itself, which is an oil, which is a lipid. Here's a typical example of membrane proteins in situ. Now, one can nevertheless obtain structural information about this membrane protein. So one thing you have to remember is membrane proteins are very difficult to crystallize, and that's because they have hydrophobic surfaces, which, whereas in a crystal, the proteins tend to be in a hydrophilic environment, and therefore they're very difficult to crystallize. But it's obviously membrane proteins like to exist in membranes. So if we could devise an experiment where the membrane proteins are illuminated while they are within a membrane, perhaps we can determine the structure of the membrane. So here's an idea for doing it. Suppose you create what's called a black lipid membrane. This is a membrane stretched across a hole in a material, and it can be thinned such that the membrane is a single bilipid layer. So the membrane would be one protein deep, if you like. Now, as I said, in general, with something like a K-channel protein, a potassium channel protein, or an ion channel protein, they tend to orient themselves in such a way that the central pore lies perpendicular to the membrane. And so they take up an arrangement rather like this. Now, if incident X-rays come in this way from one side of the membrane, one can imagine a detector on the other side which will measure the diffraction pattern. Now, in general, even with the XFEL, it's not possible to focus these X-rays down to the level of an individual protein. So you will be hitting multiple proteins here. Now, the multiple proteins differ in orientations about the normal to the membrane by random angles. So what one sees here in a diffraction pattern is the average of the intensities of all of those different membrane proteins. Now you might say, of course, you see the average of the amplitudes, but because we assume that these membrane proteins are in random positions in the membrane, the equivalent of averaging amplitudes is about the same as averaging intensities. So that's the idea for an experiment. Now, now the point is that these diffraction intensities are not sensitive to the positions of the particles, since they contribute only to an unmeasured phase. However, the orientation of the particle does have a strong influence on the diffraction pattern. So when many particles contribute to a diffraction pattern, you can add the intensities as if the particles are in random positions, and this diffraction pattern of n particles is the diffraction pattern of each particle rotated by random angle. So what we're going to do is to use the idea of intensity correlations in order to recover information about these randomly oriented particles. Now, this method of intensity correlations is very powerful and has been used in a number of different fields already. Hanbury, Brown, and Twiss used this method in astronomy for intensity interferometry in radio astronomy. And they used it to find the phase difference between two beams of light from a distant star from measurements of their intensities, amazingly. The method has also been used in the technique of X-ray photon correlation spectroscopy, XPCS, and this measures the time dependence of the density fluctuations of a liquid at various length scales. What we are going to use it for is to extract the diffraction pattern of a single particle from that of multiple particles in random orientations. Now, it's easy to explain this in 2 dimensions, in 1 dimension less than the situation we usually encounter in the X-ray free electron laser. I'll come to that case also shortly. But first, I want to talk about the case 1 dimension less. This is where the particles are in random orientations about a single axis, but the diffraction patterns are 2-dimensional. Now, if on each diffraction pattern you have 2 peaks, let's say A1 and A2, the way to find the intensity correlation function is to take a copy of this with peaks at A primed and A primed 1 and A1 primed and A2 primed, and then move one relative to the other. So if you do that, in this situation, of course, there's no overlap between the peaks, and the product of these intensities and these intensities is 0. That's what you see here. That's what you see here. Now, as you move the relative positions of the peaks on one copy relative to the other, you might reach, say, this situation where the A1 is coincident with the A2 primed, and then you will get a noticeable intensity contribution to what I call the correlation function. Now, as you keep moving it, the intensity will get higher when both the peaks overlap, and they'll get lower again, and they finally go back to 0 when there is no overlap. So the question is the following. So this is the way one constructs a C2 correlation function. And another way to write it is like this. Now consider the same correlation function, but this time where you have 2 particles. Okay, let me just see this. Right. Okay, so A1 and A2 correspond to the peaks on one of the diffraction patterns, and A1 primed and A2 primed. I'm sorry. All right. So if you look at the outer ring, we see A1 and A2. These are both peaks from one particle, and B1 and B2, both peaks from a second particle. Now, these particles are in random positions relative to one another. But if I take a copy of the distribution in the outer ring and put it on the inner ring, and then move the inner ring relative to the outer ring. In this situation, of course, there is no overlap. In this situation, there is one overlap. There are two overlaps, actually. In this situation, there are four overlaps. In this situation, there are two, and then we back to no overlap at all. Now, what I want you to realize is that this distribution is exactly, this distribution here is exactly the same as what we had on the last slide, except for the magnitude. So it's the same kind of distribution, except multiplied by n. In this case, it's multiplied by 2 because there are two particles. So one can recover a distribution as a function of angle in the correlations, which doesn't depend on the number of particles, doesn't even depend on the relative orientations of the particles. You always get the same distribution, but of course it's multiplied by a factor of n, where n is the number of particles. What one assumes, one normalizes that. Now, how do you get useful information out of this? Now, as I said, this correlation function can be found for any number of particles. And if you got a large number of particles, the correlation function will be the same, at least in 2 dimensions, in this number of dimensions. So we have this thing called the correlation function, which is defined as the product of the intensity at one particular angle times the intensity at that particular angle multiplied by d phi, and then this is integrated over d phi, and so the correlation function is a function of delta phi. This is delta phi. Now, this correlation function, as I said, is the same whether you have one particle or whether you have many. That's the so-called 2-point correlation function. One can also define a 3-point correlation function, as was done by Pedrini and Curta. So this is a function, this is a product of an intensity at a particular angle phi, at another angle phi plus delta phi 1, another angle phi plus delta phi 2. But you integrate over all the phi's, so the left-hand side does not depend on phi, but it depends on the phi 1 and phi 2. This is what I call C2, C3, Q. Q is the resolution ring that you're talking about, and it's a function of two angles, delta phi 1 and delta phi 2. Now, it can be shown that the C2 function can be written in this form, Bm times exponential I delta phi, and the C3 function can be written as Tm times this. So you can find the B's and the T's from the C2s and C3s by Fourier transformation, like this. But that's not enough. So suppose you find B1 and Bm and T, M1, M2. Now Bm is the product of two of these circular harmonic expansion coefficients of the intensity of a single particle. And the T is a product of three of them. Now, it's clear that by taking the square root of this equation, one can find the magnitude of Im as being just the square root of the Bm. But that's not enough. Now, in order to find the complete circular harmonic expansion coefficients, you need not only the magnitude, you also need the signs of these quantities. These quantities are real, by the way, so they are only uncertain by sign. Now, the way we do that is to use this equation, which says that the correlation Tm1, M2, which can be found from experiment, is equal to the product of three of these things. Now, this means you can find all the Ims corresponding to a particular reference shell, Qref. And the way we do this is the following. Now, just rewriting this equation, we can write this as Im1 plus M1, M2, T times this. And if you look at the right-hand side, all the quantities on the right can be known if you use an iterative algorithm. So this is what I mean. if I take I of 0, I of 0 generally has a phase of 0. So I of 0 has a known phase. The I of 1 has a phase which determines the overall particle orientation. And this is an experimental quantity. So if you start with, let's say we start with I1 here and I1 here, one gets I of 2 here on the left-hand side. Then you go back, you put I2 here, put I1 here, then you get I3, and so on. So you can keep increasing the index M by this procedure because the T's are experimentally known. So by this means, you can find all the IMs corresponding to a particular resolution ring QRef. Having got that, you then need to find the IMs corresponding to different resolution rings. And for that, we can use this equation, which comes from the pair correlations. And rewriting that, you can write IM equals BM for an IM star. And because you know this from experiment and this, you assume you know all the IMs for a particular reference shell, you can find IM. So this is a pictorial representation of this. We need to find all the values of IM of Q. Now this depends on two parameters. One is M, which increases this way, and one which is Q, which increases this way. Now, as I said, using the 3-point triple correlation function, you can find all the different M values. So you can find all the different M values for a given QRef. And then using the pair correlation functions, you find all the different Q values for those M's. So by this means, you can fill out this entire matrix of IM of Q values. Now, having obtained these IM of Q coefficients, it is possible to reconstruct a single particle diffraction pattern by just doing this sum, because that's the definition of the IM quantities. These refer to a single particle diffraction pattern. So by this procedure, we have found the coefficients IM, Q, and therefore we can construct a single particle diffraction pattern. And we can get a projected electron density by phasing these intensities and by taking an inverse Fourier transform. Now, I should address one question of whether the fluctuations from the wax term affects this. Now, what I mean by the wax term? What I mean is this. Suppose you have an amplitude from particle I as being AI and amplitude from particle J as being AJ. Then you need to sum these products over all values of I and J. Now, this involves diagonal terms and off-diagonal terms. The n-squared off-diagonal terms have random phases because these are randomly positioned, random phases, and this tends to make their sum tend towards 0. But the fluctuations in the off-diagonal terms tends to go as n because there are n-squared off-diagonal terms. But the diagonal terms, which produce the signal that we want, which produce the correlation functions that we want, of the same particles, have only different orientations, these signals also go as n because there are n diagonal terms. So is there a problem? No, because the correlations C2 are an average over many diffraction patterns. The point is that the wax fluctuations from each diffraction pattern are random in sign, and the average over d diffraction patterns goes up as the square root of d times n. However, the signal is always positive and grows as d times n. Therefore, the signal-noise ratio goes up as square root of d, and the signal-noise improves as the correlations are averaged over a larger number of diffraction patterns. By the way, this is the same conclusion that was reached by Kirian et al. In a paper they published some years ago. Now, averaging the correlations over different diffraction patterns breaks the dependency of the wax signal on the square of the total number of particles and overcomes this problem. Now, here I want to show you some results that's part of the thesis work of one of my students Fatemeh Jamali-Dilan, although she was helped a lot by Peter Schwander also. What we did was we took this K-channel protein and calculated the diffraction pattern that would exist from a large number of randomly oriented patterns. And of course, this looks like a set of rings. Now, by calculating the angular correlations of these and subtracting the mean, we obtained some angular dependence here, which led directly, eventually, to the diffraction pattern of a single particle, which looks like this. And then once you reconstruct a single particle diffraction pattern from this multi-particle one can apply a phasing algorithm and obtain this picture here. This is supposed to be the projection of a potassium channel protein found from these randomly oriented patterns, and you see that this protein has these levers, which are believed to be almost of atomic dimensions, and cause the opening and the closing of the pore. Now, in case you think that this is only applicable in this lower dimension, I want to show you that it is actually applicable to higher dimensions also. Now, this is a typical experiment that is performed at an XFEL. We have particles incident. We have an X-ray beam from an XFEL intersecting a particle beam, where the particles are in random orientations. And each particle gives rise to a diffraction pattern, which is measured, and you measure about 100 of these diffraction patterns per second. And as these different particles pass through, we see diffraction patterns of the individual particles in random orientations. That's of course an oversimplified picture. In reality, one uses some kind of injector, and this is an early injector that was used by John Spence and group. And what this injects is a set of droplets, each containing the proteins that we are interested in. Okay, so now I want to talk a little bit about the feasibility of such an experiment. Now, an XFEL can be focused down, and this design specification of the LCLS, you can supposedly focus it down to 0.1 of a micron, which is about 100 nanometers. But notice that 100 nanometers is still way larger than the size of a typical protein, of a small protein at least. A typical protein may be 5 to 10 nanometers in diameter. So inevitably, even with the smallest beam size you can get at an XFEL, you will probably hit more than one particle at a time. Now I just want to give you some calculations. We can work out the total scattering cross-section of an electron. This is something like this. Now, if you take a small protein, such as photoactive yellow protein, which has 1100 atoms or 7,000 electrons, the total scattering cross-section will contain about 7,000 electrons, and therefore will be about 1.82 times 10 to the minus 2 square nanometers. Now, a typical XFEL pulse contains 10 to the 12 photons, but these are focused down to about 10 to the 4 square nanometers. So the number of photons per square nanometer is about 10 to the 8. Now, okay, so now the cross-section of a protein is about, as we worked out here, it's about 1.82 times 10 to the minus 6 square nanometers. So the number of photons scattered by each protein is the product of this number times the number of photons per square nanometer, which is about 10 to the 8, and this gives about 182. Therefore, the volume of liquid illuminated is about 10 to the minus 20 cubic meters, but typical concentrations are about 10 moles per cubic meter, Avogadro's number is about 6 times 10 to the 23 molecules per mole. Therefore, the number of molecules illuminated is about 6 times 10 to the 23 times 10 to the minus 20, which is about 6,000 molecules. It should be noted that Kerian et al. Have reported success with at least 64,000 particles in random orientations about a single axis parallel to the incident beam. So we think this correlation method can handle 6,000 molecules. But a greater problem would be that one needs to scatter more than one electron. At least two electrons, at least two photons have to scatter off the proteins in the same orientation for you to get a useful correlation. This may be a concern with only 182 total photons per protein, but we have to remember that this is a small protein of 15 kilodaltons. Actually, this should be 400 kilodaltons. A typical protein that people have considered as like 500 kilodalton protein, and then the probability will be, well, it is quite a bit higher than this. It will be several hundred times higher than this. And the probability of measuring a correlation function is therefore reasonably high. And also we average over a large number of patterns. So even if the correlation function cannot be easily measured on any one diffraction pattern, it can be measured by averaging over a large number. Now, what do I mean by correlation? What is the input to the algorithm? The input is what's called C2, which is the product of the intensity on one diffraction pattern of the intensity at a certain resolution ring Q and angle phi, and resolution ring Q primed and angle phi plus delta phi. Then you subtract the mean. Subtracting the mean, all it does is it removes the DC term from this. Okay, so this is the basic quantity that we use for recovering the structure of the protein. Now, notice that neither the magnitudes nor the number of such quantities grows with the number of diffraction patterns measured. This is good because with the vast amount of data that's going to be measured at an XFEL, this is a method of data reduction. Now, let me tell you why these correlation functions are so important. Now, suppose we have a single particle. I'm only considering a single particle right now. And we consider so a single particle has a diffraction volume, which is the Fourier transform, if you like, of the electron density modulus squared. Now, this diffraction volume will be a three-dimensional distribution of intensity, and it can always be written as a spherical harmonic expansion in this way. Now, the intensity on one of these evolved spheres is simply given by this quantity here. Now, if you got a different sphere oriented in a different way relative to the first one, it will be the same quantity but multiplied by this Wigner rotation matrix, where the quantity alpha is supposed to represent the three Euler angles of rotation. Now, okay, so let's calculate these quantities. So the angular correlation function will then consist, in general, of the intensities on any one particular diffraction pattern multiplied by a Wigner rotation matrix multiplied by the intensity at another position, another diffraction pattern. And if you look at this expression here, it helps a lot to first do the integration over all possible orientations of the particle, because this particular integral, which is the integral of the products of representations of the SO3 group, these satisfy what's called the great orthogonality theorem, which allows you to simplify the expressions on the right here, which otherwise have a huge number of indices. I think they have 8 indices. But because of these delta functions, the whole expression reduces to the following. introduces to C2 is equal to some Legendre polynomial multiplied by this quantity B, which is a quadratic function of the spherical harmonic expansion coefficients. Now remember, if you could find these coefficients, you can reconstruct a diffraction volume. But what can easily be done from the data is to invert this equation and thereby get the B's. So this is what I mean. This is what the C's look like roughly. There's a peak in the corner, the central peak, and then there's another peak here, and depending on which Q's you're using, you get a different pattern. Now, as I said, the C's satisfy a relationship like this. So by inverting this equation and obtaining the B's, one can obtain the quantities BL of QQ primed. Now, by the way, it's easy to take account of the curvature of an Ewald sphere with this formalism. It's given by this expression. I won't go into that. Now, as I said, what we find are these quantities B, which I said were quadratic functions of the spherical harmonic expansion coefficients. Now, how is this useful for determining the structure? Well, so far, we have only used it for symmetric cases. There's the icosahedral virus. Viruses are generally said to come in two varieties. One is an icosahedral variety, the other is a helical variety, and we can actually solve it in both of these cases. In the icosahedral case, the diffraction volume is given by this expression. The B's, which we can extract from experiment, are given by this quadratic expression. But if we use what are called icosahedral harmonics, which means the intensity distribution on the three-dimensional diffraction volume is a sum of icosahedral harmonics. So it has icosahedral symmetry. That's what it means, because each of these icosahedral harmonics has icosahedral symmetry. Then one can write, well, each of these icosahedral harmonics is a linear combination of the spherical harmonics, but it's a linear combination over the magnetic quantum number m. And as a result, the icosahedral harmonics only depend on the quantum number L. This means that it's the same quantum number that characterizes the B's, which are found from experiment. And the BLs can be written as a product of these two. Right? So if you want the magnitude of G at any particular reference shell, you just need to take the square root of the B's. Now, these quantities happen to be real, so we only need to find the signs, and we do that via the triple correlations. Actually, in this case, the triple correlations look something like this, where B is some known function, and the quantity on the left is found from experiment. The magnitudes of the quantities on the right are known, but their signs are not known. So the idea is to work through all possible combinations of signs on the right-hand side until you get best agreement with the left-hand side. So this will give you all the magnitudes and signs of the GL quantities on a particular reference shell. Then you can go to a different shell in the same way I described before by using the pair correlations, which allows you to find the L's corresponding to a different Q, and therefore you can find the oversampled diffraction volume from this expression. The electron density is then found by an iterative phasing algorithm, and to our surprise, it really works very well. So this idea for simulations of randomly oriented diffraction patterns from an icosahedral virus, we chose the smallest virus that we know of. That's a satellite tobacco necrosis virus, and we simulated diffraction patterns, a large number of them, and then ran this algorithm through, and finally what we get is a picture like this. And what is more, it turns out that this is a hollow shell. Now you might say that it's not surprising that you get an icosahedral shape, because that's the assumption. But the hollowness of this shell is not an assumption. That comes directly from the data, because any structure perpendicular to the angular coordinate is not implied in the icosahedral assumption. Now, yeah, I don't know whether I can show that. Never mind. I now want to go on to consider a helical virus. Now, with the helical virus, we can also solve it for another reason. Again, we make use of symmetry. Now, in the helical virus, if you look at the intensity coefficients of the spherical harmonic distribution, these intensity coefficients have m equals 0 for low resolution. And therefore, when one can find the magnitudes of the IL0 coefficients for a particular reference shell by just taking the square root of the left-hand side. Now, once again, these quantities are real, so we only need to find their signs, and we do that as before with these triple correlations. So the left-hand side is known from experiment. Everything on the right-hand side is known except the signs. So we consider all possible combinations of signs until we get best agreement with the left-hand side. Again, having found the spherical harmonic expansion coefficients for a particular reference shell, we propagate to a different shell by using the pair correlations, and then we construct an oversample diffraction volume. Again, when we do that, we get what looks like a fiber diffraction pattern with a set of layer lines. Due to the fact that a fiber is oriented this way, it will have a periodicity along this direction. And what is more, we can take the diffraction volume and apply a phasing algorithm, and we get something that looks like this. I admit this is still a low resolution image, but we are working on this. We are working on improving the resolution. So this on the left-hand side is the known structure of this virus, and the right-hand side is what we are getting, and I think it's a fairly good approximation to that. But we're working on improving that. Now, I wanted to mention one thing. There has very recently been an algorithm which supposedly goes directly from the experimentally measured quantities, the B's, to an electron density estimate of the sample. Now, so how does this work? So basically, what it does is it constrains the. So what we want to get is the intensity distribution, the spherical harmonic expansion coefficients. We know the B's are quadratic functions of the spherical harmonic expansion coefficient. So the idea is to start with an initial density estimate, let's say rho 0, which can come from the icosahedral approximation, and then take its Fourier transform. This will give an initial value of the amplitude. Now, the modulus square of the amplitude is the initial value of the intensity. And hence, we can calculate the spherical harmonic expansion coefficients of the intensities, and hence, we can calculate B. Now, this is for our estimated initial estimate of the electron density. Of course, it won't be right. So what we want to do at this stage is adjust the magnitudes of the ILM coefficients such that they agree with these experimentally measured B's. Now we don't touch the phases of these coefficients. Just as in a normal phasing algorithm, you adjust the intensities when you go to reciprocal space, but you don't touch the phases. Right. Now, this specifies I and okay. So once you have the ILMs, you can construct the I by the usual formula, sigma ILM, YLM, whatever. And then the magnitude of A is obtained by just taking the square roots of these intensities. Now, so we can get the magnitude of the A's corresponding to the experimental values. Of course, we don't know the phases. So what I suggest is we keep the phases from the previous iteration and calculate the inverse Fourier transform of this. calculate of the A's. This will give us a new electron density. The electron density is then constrained by some kind of real space constraint, for instance, shrink wrap, and then you go back to this stage. So once you get an electron density, we can recalculate an amplitude, and we can go back to this step and repeat the process. So essentially what this is a phasing algorithm for the spherical harmonic expansion coefficients. We adjust the magnitudes by the experimental B values and adjust the phases by using some kind of support constraint, for instance, shrink wrap. This is more or less what a traditional phasing algorithm does, except instead of A, we determine ILM in magnitude and phase. So these are some results of a paper that Peter Zwart sent me. It has been submitted to the proceedings of the National Academy of Sciences, and it shows actually remarkable effect. So on the left-hand side is you have the three-dimensional structure of a protein. This is looking straight down when it says five-fold symmetry, and this is looking at it sideways. And on the right here is what is reconstructed by this algorithm. And you see, if you compare these, there's a remarkably good agreement if you assume five-fold rotation symmetry. Now, yeah, one other thing I want to mention here, that that this algorithm is so useful because what you find is the correlation function of a collection of particles. Right? So, I mean, it's more or less the same as one particle. Now, what I want to show here is that it's almost inevitable that you will illuminate multiple particles, unless you're talking about very, very large particles such as virus. So if you form a droplet from a solution of proteins, and let's take P by P, well-known photoactive yellow protein, and what we want to do is to maximize the concentration, to maximize protein scattering as opposed to scattering from the buffer or the water. And this corresponds to a concentration of about 10 millimolar per liter, or 150 milligrams per milliliter. And if the spot diameter, so the smallest spot diameter from an XFEL is about 0.1 of a micron, which is about 10 to the minus 7 meters. Cross-sectional area will be this. The minimum droplet diameter reported is about 0.3 of a micron. So the volume illuminated by an XFEL is typically of the order of 3 times 10 to the minus 21 cubic meters. The number of moles illuminated is therefore about 10 to the minus 20, 3 times 10 to the minus 20 meters. Avogadro's number is about 6 times 10 to the 23 molecules per mole, and therefore the number of molecules is about illuminated is about 10,000 or so, maybe 1,000. And even with a reduced Sachs concentration of 10 milligrams per millimole, which is what's used in Sachs, and a 500 kilodalton protein, this number should be divided by 500 and by 515, which still gives about 20 molecules per droplet. So it's almost impossible to illuminate a single protein by this method with an XFEL. Of course, you can illuminate single viruses. So for a liquid jet, the good news is that multiple particles contribute to a correlation coefficient and therefore gives better signal. The bad news is particles are randomly oriented. Nevertheless, as we have seen, it's possible to extract the structure. Now, I want to conclude by giving one final example of a time-resolved experiment, a possible time-resolved experiment performed in a liquid jet that contains many of these molecules, these protein molecules, say P by P, in solution in random orientations. And the experiment will consist of hitting the proteins with a laser a short time before it is hit by an XFEL beam. So the proteins will be in some excited state corresponding to that length of time since photoexcitation, and then it is probed by an XFEL beam, and different numbers of proteins will be probed in all orientations, and one can use the methods that we described earlier to find the B's. Now, what I want to point out is that the B's, although you find the B's by this method, this is still very useful for finding the time-resolved structure. The point is one can take this expression for B and take the variation of both sides, take small variations of the delta, the ILMs and the delta B's, and we get this equation. And then because the intensity is the modulus square of the amplitude, one can get this equation. You differentiate once again with both sides, you get this equation, and then the intensity, the spherical harmonic expansion coefficients of the intensity distribution are given by this, and the spherical harmonic expansion coefficients of this are given by this integral. And what one does is one takes the ILMs and the delta ILM, substituting into here, and because this quantity depends on the delta A quantity, which is related to the change in the electron density of the particle, one can directly relate the change in the B quantities to the change in the electron density of the particle. So this might possibly provide a method of performing time-resolved structural experiments on uncrystallized molecules in solution. Now, the correlation function filters out uncorrelated signals. So these are the advantages of use of correlation. Correlation function filters out uncorrelated signals, i.e. from background. So signals from background will tend to be uncorrelated. Uncorrelated interference fringes from randomly positioned particles. Expected mean photon per count for high resolution pixel for 500 megadalton protein is about 10 to the minus 2. The expected value of the product of two such mean photon counts is about 1.6 and 10 minus 3. The value of this product would be expected to reach this quantity for given delta 5 and average over a large number of randomly oriented particles. Each diffraction pattern will have a minimum of 20 particles with perhaps 10 to the 6 dPs measured. That's the expected value of the correlation function for any value of delta 5 would be expected to be reasonable. Now, what about the effects of noise? The signal resides in the correlated scattering from the same particle. If there are n particles illuminated, the signal will be proportional to n. The uncorrelated scattering from different particles goes up as n squared, and this will be the dominant source of noise, which goes up as the square root of n. This is consistent with the results that Kirian et al. Found a short time ago, that the signal to noise goes up as n upon n, and therefore it seems to be independent of the number of particles per snapshot. However, even Kirian et al. Found in their paper that the signal-to-noise ratio actually goes up as the square root of m, where m is the number of diffraction patterns averaged over. Thus, although the signal-to-noise cannot be improved by increasing the number of particles, they can be improved by increasing the number of diffraction patterns that can be averaged over. I won't get into that. These are some results that my postdoc Kanupriya Pandey obtained a short time ago. Now you might first think that the correlation signal, there's hardly any correlation signal, because when I looked at that multi-particle diffraction pattern, it looks like a set of rings, set of unfeatured rings. But the whole point about the correlation function is to subtract off the mean. And when you subtract off the mean, these small intensity variations do show up. And what is more, we found that the single particle signal becomes almost the same as the multi-particle signal. Yeah, and I think Rick Kirian has also written a program that demonstrates this. If you average over enough diffraction patterns, and this holds whether or not you assume coherent scattering. Now, finally, I want to show some results that Kanupriya obtained recently for various numbers of randomly oriented particles, and she found that the difference density is almost exactly what you would expect for certain movements of p by p. Here, the green lobe corresponds to an increase of electron density corresponding to a chromophore which has moved in that direction, and the red lobe corresponds to a decrease in electron density corresponding to the position that the chromophore moved away from. Yeah, I just want to point out one final thing. This idea of finding small differences by this method could possibly be used for improving a good mask that you obtain of a molecule. So suppose we obtain, this is for a small molecule, chignolin. We created a mask only consisting of ones and zeros. Then we applied this algorithm to find the delta B's and hence the delta rhos. And this is the difference density, the delta rho. When you add this to the rho, we get a nice looking final density. So this possibly has other uses. Now, finally, I come to my conclusion slide. It's possible to think of the method of angular correlations as a multi-particle method. And it does so because it does not ever try to find the relative orientations of particles corresponding to different diffraction patterns. What it finds is the average, the total correlations or the average correlations of all the diffraction patterns. And because it finds an average correlation, it can be used also for multiple particles, because the average or the total correlations from all particles, from many particles, is the same regardless of how many particles there are. Now, the reason I think this is important is because this is a true multiple particle method, and it may not be possible to focus down to the level of a single particle. If so, a multiple particle technique is a must. However, because it can deal with multiple randomly oriented particles, this should not disqualify it as a single particle method, because I think you saw that the whole derivation of the formula started with a single particle. So it should be still applicable to the SPI initiative, the single particle initiative at the LCLS. Yeah, so this method can be done for random particles in 3D, in the SO3 geometry, but also for random orientations about a single axis, which also have possible applications, can be used to determine the projected structure of a membrane protein in situ, despite the fact that the individual proteins are not aligned. So this avoids also the need for crystallization. And solutions have been demonstrated, at least with simulations, for icosahedral and helical viruses. And the new algorithm just proposed by Donatelli, Zwart, and Sethian may make solutions possible more broadly, because essentially, I said you can find those B quantities very easily from the experimental data. Now, whether we can get from the B's to the density is another matter. So far, we've had some difficulty, and we have had to use symmetry arguments or in the time resolved method, a known structure, which is very close to the structure that we want. But if this algorithm works, and it's still very early days yet to know whether it will, if it works, it will mean that we can find the B's, and from that we can find the rhos of an arbitrary protein on arbitrary substance, whether or not these are single particles or multiple particles in random orientations. And this is robust with respect to uncorrelated noise and shot noise. And it can also be used, as my last example showed, for small time-resolved structural variations, and perhaps can be used for determining molecular movies of chemical reactions, even though you don't actually have a crystal of particles in solution. Okay, I think that's about all I wanted to say. Thank you very much.